Okay, good evening. We are going to be looking at types of reactions today, and we're going to try to get through all of them if we can. This lesson is going to go for about 40 minutes. We're going to take about a 15-minute break and then reconvene again in the 15 and carry on. Please, at any time, feel free to ask questions, and I will try to answer them as you ask them. Okay, so types of reactions. So we talked last class about when balancing, we need to follow the law of conservation of mass and stating that whatever we start with mass-wise, our products have to match up in terms of masses, okay? And that kind of brings up to the following point, that matter cannot be created, nor can it be destroyed. Okay, so in terms of chemical reactions, all chemical reactions involve either some kind of release or some absorption of energy. Okay, so sometimes we might need to heat things up in order to cause a reaction to take place, or once a reaction takes place, it might give off, let's say, a bunch of energy. That energy that we can give off be in the form of a release of light, electricity, or even sound. So we have two types of reactions, but this is more on the energy level. These aren't the types of reactions that I'm talking about for chapter 5. But within these types of reactions that we're going to see in a moment, they can either follow in terms of the energy, either be exothermic, okay, either exothermic here, meaning that energy is exiting, so it's giving off. Okay, so the idea that some kind of energy reacts, generates heat on its own. Okay, so exothermic reaction, some form of energy for the reaction to start, and the reaction will continue and generate heat all on its own. So think about lighting a stick of dynamite. Okay, so you light that stick of dynamite, that wick burns, and it carries off right through, and it eventually kind of will explode. Other ones here, burning of fuel, rusting of iron, all it needs a little bit of energy to kind of get something started, and then eventually it will proceed on its own. Okay, so the next energy involvement are, we're going to ignore that, are endothermic reactions. So endothermic reactions require some kind of input, so inside. So we've got to input energy to cause the reaction to carry forward. And the thing is, with an endothermic reaction, we continuously have to be putting in energy. We don't just put it in a little bit and then watch it kind of carry on. It's got to continuously be put. Here's a great example here, right up at the top, cooking. Right, when you cook something, you're constantly adding heat to something until it's ready. Okay, so that's considered an endothermic reaction. So remember, these two types, exothermic and endothermic, are strictly related to the energy production or energy exit or output that a reaction will kind of give off. And all reactions will require some kind of energy, whether it be on the endothermic or on the exothermic side. Okay. So law of conservation of energy, as I'm showing here with this Newton's cradle, and it's not animating, but if you watch the slide, it should animate. So the law of conservation of energy states that in a physical or a chemical reaction, energy may be converted from one form to another, but the total amount of energy remains constant. Okay, so in this case here with this Newton's cradle, as that ball that's been lifted, okay, as that ball that's been lifted comes back and hits all of them, it will distribute only the amount of energy that it has. So that amount of energy kind of carries forward to be able to hit the Newton's ball on the opposite end to carry that over. And then eventually that one comes back and hits and knocks the other one, and it goes back and forth, back and forth. Okay. Some of the reactions here when it comes to burning of hydrocarbons found in organic chemistry. These are all typical exothermic reactions. So in a lot of these exothermic reactions, thermal energy is what's given off, right? So a lot of these hydrocarbons are used to help burn. So there's perfect sources of crude oil and natural gases that help heat our homes, our businesses, schools, used for transportation, whatnot. But all that exothermic energy is what helps create that thermal energy that's being created. Okay, so let's get another. All right, let's actually look at the first set of types of reactions. And here we go. We're going to look at synthesis reactions. So as I said, the synthesis and decomposition. So 5.3 and 5.4 that probably have some tricks to it. We're going to take away all the tricks. Okay, so we're going to try to keep it nice and simple to help us move on with this course, just due to the nature of this the course. But you'll see what I mean when we actually go through the synthesis reaction. So synthesis reactions here, typically we're combining two reactants to form a combination of products. Okay, so in this example here, we've got some kind of A element or A atom and some kind of B atom. And in the end, we're going to form a combination of all of them together. Okay, and that's considered a synthesis. So to synthesize means to make. So we are making something. So we're putting two things and we're making one thing at the end. So notice we can either have two or more things that we are inputting for our reactants. And in the end, we are only forming one product. So that's the hint. Okay, that's the hint. We are forming one final product in the end, and that is considered a synthesis reaction. The next type of reaction that we're going to see is decomposition. And decomposition is the exact opposite of this synthesis reaction. So in a decomposition reaction, we're going to start off with one compound. And in the end, we are going to break it apart. We are going to break it apart into its respective pieces, whether they be two diatomics, whether it be a metal, non-metal. You'll see with some of the examples what we're talking about. But what we're doing is we're breaking it apart. So various synthesis reactions. Here are the 6 types of synthesis reactions that can take place. The only ones I want you to worry about are the following. The first one here. So that first one we want, this fourth one, this fifth one, and this sixth one. We're going to ignore these two just for, I guess, for this course to kind of alleviate some of the stresses that we're going through with this course. Not saying that they're not important, but we're not going to, the other ones will kind of give us a better understanding of these types of reactions. But understand now, as I mentioned just moments ago, these are synthesis reactions. Remember what we said? Decomposition reactions are the exact opposite. So all 4 of these types of reactions, its reverse will be the decomposition. So instead of 2 elements will burn to form a binary compound, if we're looking at it as a decomposition, this decomposition reaction will break apart, right? Will decompose into those two elements. In this example here, we've got a metal, this last one, sorry, metal carbonate reacts with carbon dioxide and water to form a metal hydrogen carbonate. But if we decompose it, so if we can decompose this metal hydrogen carbonate, it will decompose into water, carbon dioxide, and metal carbonate. So you're going to need to practice all these in order to kind of give yourself a better understanding of what is expected of you. I will also kind of go through which sample problems you should know and which ones you can kind of ignore, because if I tell you to ignore it, it means that they fall under one of these two categories. Okay, let's move on. Let's look at an example here. So here's an example. Two elements will react to form a binary compound. So we've got sodium and oxygen, right? So sodium and oxygen will come together. Okay, so we've got Na and O2. And remember, as I said last class, oxygen is one of those diatomics. So oxygen being diatomic, we write it down with that O2. It's not just O. And in the end, we are putting together sodium oxide. And now notice the formula of sodium oxide. Okay, remember, and I'm doing a quick recap of this right now, but your ability to put together formulas is vital here, because to know this sodium oxide, right? If we're combining sodium and oxygen together, we're going to form a metal and non-metal combination, right? Ionic compound. The non-metal has the IDE ending, right? But now, how do I go about putting this together? And sometimes students will be like, well, hey, I have Na and I've got O2. Why don't I just put it together like that? But because to put an ionic compound, you need to follow that 5-step crossover rule, right? Identify metal, non-metal, right? The symbols, charges, crossover, remove the charge, simplify, remove the ones, and that's how we get, okay, that's how we get this actual formula that you see here, Na2O. And the last step, once you've actually put together this is, as we said, our skeleton. We said this last class, skeleton, sorry, skeleton equation. Then we have to balance it. Remember, so once you put together your equation, you still need to balance. Equations always need to be balanced. Okay. So let's clear that and move on. Then I balance it. Ignore the 2 here. For some reason on the display, it's acting up. That 2 should be in between the Na and the O. And here we have the example. It's been balanced. Next one, we're going to skip this one because this is one of the ones I said we weren't going to do. This is another one we said we weren't going to do. Okay, so here we have the next synthesis type of reaction. So whenever we're combining a metal oxide with water, we take the metal and we combine it with just hydroxide. Remember what we said last class? If we see hydroxide on one side, look for water on the other side. You're not going to use that method to balance these ones, unfortunately, but it pretty much kind of helps reinforce that that trick that we talked about last class when it came to balancing. Okay, so we look at this, right? So if I've got zinc here, zinc oxide plus water, what am I going to form? I'm going to form a zinc hydroxide. So that zinc hydroxide, what's the formula for a zinc hydroxide? So look at this end result, Zn, open brackets, OH, close the brackets, put that 2. Where'd that 2 come from? Again, just a quick recap from 4.1, 4.2. That 2 came from the charge from zinc. And the charge of hydroxide is a -1 that gets crossed over. The last thing is to balance it. And I do believe this is already balanced. Okay, so you can either write the skeleton equation as is, or you can write it down as or right underneath your skeleton equation, already balanced. Understand, I don't give the mark for writing already balanced if I don't see a skeleton equation. Because some students will be like, nah, I don't really want to balance, so I'm just going to write already balanced for all of them. To get the mark for the already balanced, your skeleton equation must be correct. Okay, so let's move on. Okay, so a non-metal oxide, non-metal oxide and water. These are the ones are somewhat easy, but you need to first identify. You need to be able to identify. So you're not going to get this wording part. Right? You're not going to get this wording part. You're going to get something like this. Okay, you're going to get sulfur trioxide reacts with water. That's what you're going to get. You got to figure out that this is a synthesis reaction, right? So you're going to need to refresh yourself with this knowledge. So when you're putting this together, you are going to form a polyatomic acid. Remember what we talked about with acids? Acids start with H. Okay, acids start with H. They'll have the AQ at the end. But the trick is, for these ones, is this. You take the H's, and the H's will be given to you. There's the H's. So we're going to have an H2. And then the other trick is put together everything that's left right after it. So there's one S, and there's 3 oxygens here, 1 oxygen there, total of 4 oxygens. So here's a trick with these synthesis reactions. I'm going to make them nice and simple where they're always already balanced. Okay, so the end result, there it is. So all we're doing is just putting it all together, make it look like a polyatomic acid. Okay. So that's how I like to think how simple it actually is in terms of these ones. Okay, but the trick part is really being able to identify that it actually is this type of reaction. Okay, and the last one that we're going to look at for synthesis is metal carbonates reacting with carbon dioxide and water to form a metal hydrogen carbonate. Okay, this 3. Let me put it. Let me write it down at least here. Okay, ignore that. So there we have it. Na2CO3, there's our sodium carbonate plus carbon dioxide plus water. And the end result is going to be a metal hydrogen carbonate. And now quick recap of these polyatomics, how these polyatomics work. You're going to have your list of polyatomics for a test or a quiz with you. But just to kind of sometimes not requiring, let's say, all that can help speed up the process. Understand that when I do have when we are going to be doing the evaluations, there will be a time limit with the evaluations, just to kind of prevent students from communicating or even researching a lot. So you need to come prepared when we do come together for an actual evaluation. Okay, but more on those evaluations to come. Okay, so let's put the hydrogen carbonate together. Remember that if we have a metal, right, the metal is going to be the Na. Okay, the metal here is going to be the Na. We've got a hydrogen carbonate. Don't worry about the hydrogen right now. Just focus on the carbonate. Carbonate is CO3, and my pen is acting up, -2. But what about the hydrogen? So the hydrogen is not part of the metal. The hydrogen is actually part of the non-metal polyatomic. So when I add an H to the polyatomic, I lose a charge. So that charge drops from a -2 to a -1. So when I cross over, so we've got +1, -1, +1s, -1s. When they cross over, right, they're going to simplify, remove those ones. They're not actually going to be there. So the end result will be NaHCO3. There's the metal hydrogen carbonate that it forms, and of course that 2 is there because it was used to balance the equation. Okay, but the 2 wasn't there originally. Okay, at the end there are a bunch of sample problems. In terms of the sample problems to ignore, we can ignore the first one, A. G. Ignore I. Ignore J. Yeah, so just ignore letters A, G, I, and J. Okay, so when you do get a chance, please go through these sample problems. The answers to these sample problems can be found in the remaining slides. Okay, so let's look at decomposition reactions. Okay, so as I mentioned with the previous lesson, decomposition reactions are the exact opposite to synthesis. So we start off with one thing, so one reactant, and we break it apart into 2 or more products. Okay, those tricks or like some of the ones that we need to kind of be aware of. So the first one we need to know. The second one, no. This third one was no different to number 6 on the previous lesson, and 4. So 2 and 4 are exactly the same as 2 and 3 from the synthesis reactions. Okay, so so that's so all it is really, know the 4 from synthesis and understand that those 4 in the reverse order is decomposition. Okay, so let's look at some of those examples. Okay, so here we have an ionic compound, a simple ionic compound, metal, non-metal, right? All we're going to do, break it apart. So there's magnesium chloride, right? There's the formula, MgCl2. Break it apart into magnesiums and chlorine. Now, don't be fooled into thinking that this 2 here is because of this 2 here. This 2 here is because it's diatomic. This 2 here is because it's the charge of magnesium, okay, or the oxidation number of magnesium. That's why that 2 is there. And that's why I put the 2s in different colors, okay? So just remember the 7 diatomics, like I said, they start from the 7th atom, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, so that it forms a 7 from the 7th element on the periodic table, and the one that's not in that 7 is hydrogen. Others, as I've mentioned last class, I think something like Dr. Hofbrinkel or Mr. Hofbrinkel or Mrs. Hofbrinkel, whatever way helps you remember, use it. Okay. We're going to skip through that one. Okay, so here is that metal hydrogen carbonate, the last example that we were looking at in in the previous. Okay, so what we're going to do is we're going to break this down into a metal carbonate. So we're going to take the metal, which is lithium, and combine it with carbonate. And then we're going to add CO2, and we're going to add H2O to the formula. And there we have it. So there we have the Li2 and the CO3, and plus CO2 plus H2O. Okay. And then, of course, you need to balance the equation. Okay. We said we're not gonna do this one. So here we have a metal hydroxide, so a base. Remember how we said when we were doing the acid-base nomenclature, bases are anything that have the OH. So when we break apart a base, the metal from the base, okay, combines with oxide. Oh, okay. So in the end, right, we're going to break apart Fe OH and the 3 into Fe2O3. Okay, remember that the 2 in this example here came from oxygen, this 3 came from iron, and of course, then the water. This here, this 3, this 2 here is there just from the balancing. Okay. So when we're combining the metal oxide again, right, just putting together here the Fe and the O, metal, non-metal, right, the charge, right, cross them over, and that's where we got these. So I know it seems like much. What makes this seem kind of maybe overwhelming, and I'm down to the last 10 minutes, so we're going to be taking a break momentarily while I render the clip. It seems overwhelming. It's because you need to know these rules. Okay, you need to know these rules in order for them to know how to put together the equation. Okay, so and to be able to identify what type of reaction you have. Okay, so it's very important that when you are doing these, you've got to know. And again, we've only looked at synthesis and decomposition right now. We're still going to look at single displacement, double displacement, single, double, neutralization, and complete and incomplete combustion. Okay. And again, those should all be review from the grade 10 curriculum. Okay, and the last one here, the oxyacids. All it is, remember how we said, just break this apart. Remember how to form the polyatomic acid, we put everything together, but we put the hydrogen first. Here, break it apart. So remember, we form water as one of them, right? So we take out, right? Let's take out this H2 and one of these O's, and all we're left with is the CO2. Now, another thing to make note of, the order that I write these, that doesn't matter. I could have written this first and then that. Doesn't matter the order. The only order that matters is our reactant is first. The arrow goes in this direction always, and it's an arrow, not an equal sign. It's an arrow. And then what we're putting together. Okay, but remember also, if it's ionic, metals are always written first. If it's acids, we typically always write the H's first. Okay, so those are really the only stipulations when it comes to the ordering. But in terms of, do I put CO2 first before H2O? That doesn't matter if they're both on the same side. Okay, so in terms of, we're going to take a break for about 15 minutes. So take a break for about 15 minutes, work on those sample problems, test them out, see what you can get. I am going to ask if a few people I need to test out a different format. I'm being told I shouldn't be using Zoom, and so technically tonight could be our last night using this platform. Okay, I'm going to try to test out Google Meet. Okay, so I'm going to go on to Google Meet with my Papa Podcasts account. See if you can find me under in Google Meet, and we'll play around with it during that 15-minute break if you're interested in playing with it, because we're going to need to eventually get there. I'm gonna have to figure out a way to kind of get us all there, because I'd like to do a lecture style, and I'd rather not send you out to um, um, just kind of fend for yourselves and just ask questions along the way and just kind of read through my notes. I'd like to be able to lecture if I can. Anyhow, let's figure out which ones we're not going to worry about doing. Decomposition there. No, that's fine. That's fine. So don't do E. Don't do G. Don't do J, and don't do K. Okay, so those are the four letters: E, G, J, and K. Don't worry about doing those. But again, if you are interested in seeing what they are on the slides. You can see the answers; they're right after it. So please do attempt to try those out. Okay, so I'm going to wrap it up there for the first half. Like I said, we're going to go on a 15-minute break. For those of you who are interested, come on over to Google Meet and we'll play around with that. I could use an audience to see how this thing works. Okay, so I'll see some of you or the rest of you in about 15 minutes. Take care.
I hope you liked this video. If you did, do not be shy to hit that thumbs up button. And while you're clicking the thumbs up, click on that subscribe to stay tuned to my new videos. Thanks for watching.